Um, no, so I waited for 15 minutes. So since students haven't joined, I'll start. And as usual, this will be available on YouTube. So you can view it at your leisure. So today we'll be discussing problems from week 9, which is closed queuing networks, uh, lectures 32 to 35. So as I usually do, I went over the lectures myself because some topics were unfamiliar to me. And so I have prepared notes and I'll share these with you. Hopefully these will be useful. And so it's just kind of like basic notes and formulae um, that, that might be useful. So there are many algorithms that are discussed in this lecture, but I believe these algorithms, for example, the mean value analysis algorithm, that's something which I was familiar with earlier. These algorithms are very nice, and it will be really helpful if all of you try to implement these algorithms on your own using a familiar programming language like MATLAB and see how these work and get a feel for it. But as far as theoretical assignments are concerned, these algorithms are not really suited for pen and paper examinations. So we'll be discussing a few problems that kind of cover the broad concepts and yeah, don't really make you run the algorithms. So let's discuss today. We'll be discussing closed Jackson networks. So these are networks where the total number of customers here is a constant. So there is no external arrival or departure of customers. So that's why gamma I is 0. And as shown here, gamma I, that means that there are no new arrivals and there are no exits from the network as well. So Ri0 is 0, right? My apologies. Anyway, so it doesn't matter. So yes, so then in general, we can study closed Jackson networks, and we can kind of solve for the state transition diagram and solve the balance equations and all of that. But there exist algorithms that kind of help us in this process. So if we try to compute it the usual way, then it becomes a huge combinatorial problem that is difficult to solve. So there are algorithms that give us recursive formulations through which we can perform these computations faster. And so there are two algorithms, convolution algorithm and mean value analysis, which I don't want to detail right here. And then its extension into the multi-server case when there are multiple servers with different rates. And a simpler but very important special case of closed queuing networks, which we'll be studying, is cyclic queuing networks, where it is essentially tandem queues, one after the other, and then it kind of loops back from the final queue to the initial queue. So it's also a closed queuing network, but this is a special case and it has its own properties. So it's a very important network to study. So with this, we can start discussing problems. So we'll first start with generalized closed Jackson networks. So The first question is, let's say, just, thank you for this. I hope the screen is still visible. Okay, so the first question is, how do we, like, how many, let's write it, how many states are there in closed Jackson queuing network, right? So we need some parameters, right? We need to know how many. So let's say there are M nodes and K customers, right? So we want to find out how many states there are. And so we can go to the definition of state diagrams here, of the states here. And we can see that the states are defined as N bar, where N bar, comma, I plus, comma, J minus. So it's kind of defined as like the combined N1, N2, N3, Nk. That whole vector is a state. But we need to remember that these quantities N1 to Nk are not independent. They actually have a linear dependency. So they add up to N. And so that is why we won't have exactly as many states as possible. So it will actually be more like a combinatorial solution. So we have k possible partitions, right? Because there are k nodes here. Like in this formula, there are k nodes and there are n customers. So we have k possible partitions of n customers. So k possible groupings. So it kind of comes from probability and like permutation and combinations theory. So this answer will actually be something like, let me actually use the notation in the lectures itself. So we'll have k nodes and n customers, right? So the answer here will actually be, it actually comes from this relation, right? We'll have n1 plus n2 plus dot 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 plus nk equal to n. And like, so that will come out to be something like n plus k minus 1 times k, choose k. And this is the answer, right? It's a permutation combination problem. I don't want to go into the details of solving it. So okay. Some problem happened. I'll just give me a second. My iPad disconnected from the Wi-Fi, so I need to reconnect it back. Right. So it seems to be back, and zoom and share screen. Okay. Okay, I'm back. So this is a combinatorial problem. So you can think about it. I don't want to get into details here, but this is the number of states that you can have. So then the second question here is give me a second. So then again, it's again a conceptual question. So we have the routing matrix R in Jackson networks, right? So the question is, it's kind of like a true false question. So R for closed Jackson network is stochastic. So that's the question. So it's like, so the true or false. So we need to think about this a bit. So by stochastic, what we mean is something like R of n should be some function of R of n minus 1, etc. Right? So for a closed Jackson network, what we have is Ri0 equal to 0 for Ri. And also the gamma equal to 0 for all I. So nothing enters or leaves the system. And so hence it has to be a stochastic, it has to be a stochastic process, right? Because we don't have the I0 quantities that actually make jobs or customers just leave the system altogether. So it will always, so like actually this will always be something like R of n minus 1 times R. So you can actually like extend this to something like R to the power n. So this will happen because nothing leaves the network. So it will always be subjected to the same routing matrix. And so we'll have a stochastic nature of the routing matrix. So then this is, the answer is actually true in this case. So follow-up question, kind of, or like 2B, if I were to ask, which is same question, but so R for open Jackson networks is stochastic. True, false. And well, the answer for this is and so for this, we actually have this relation, right? For open Jackson networks, there has to exist some I where there is some arrival and there is some departure. So then some packets will actually come in externally from outside. And especially because of these Ri0 quantities, some packets will be forced to leave. And so once they leave, they won't be subjected to the same routing matrix again. So we cannot really write something like this. Cannot really write this. And so the answer for open Jackson networks is actually false. Right? And so that's some discussion. And on a similar note, let's do another simple conceptual idea, which is something like, okay, we have which of these conditions lead to closed Jackson network? So we have a few options here. Firstly, we have something like gamma I equal to 1, something like gamma 1 equal to 1, gamma I equal to 0 for all I not equal to 1, and Ri0 equal to 0 for all I. Then we have, let's say, gamma I equal to 0 for all I, and Ri0 equal to 0.5. Say, let's say R10 equal to 0.5, Ri0 equal to 0 for all I not equal to 1. And then C, we have gamma I equal to gamma I equal to 1 for all I, Ri0 equal to 1 for all I, and fourth, gamma equal to 0 for all I, Ri0 equal to 0 for all I. So clearly, the correct answer is option D in this case, because there are no external arrivals and no departures. This is wrong because we are clearly having external arrivals in all of the nodes, and also they are almost like forced to depart because Ri0 is also 1. So it's arrive and depart, so there's nothing happening. It's not a closed network. Similarly here, even if one node is leaking here, so there is one node that is allowing customers to exit. So it's not a closed Jackson because it's not closed. Some packets are escaping. And similarly, if we are allowing entry of external traffic at one node, it's again not a closed Jackson. So we really need a completely closed system where nothing comes in, nothing goes out. It's all circulating inside. Okay. So with that done, we'll do a few problems now. So these were some kind of conceptual questions on general closed Jackson networks. We'll now focus on the special case, which is closed cyclic networks. This is a special case of closed Jackson networks. And so that's what we were discussing, right? So there are it's like queues in tandem, one after the other, and then the last queue feeds into the first queue. So it's all a cycle, and so that's why the routing matrix is always going to the next queue for all of the nodes I for all of the nodes 1 to k minus 1, and for the kth node you just route it back to the first node, and so this is actually pretty easy to solve. And we can do some good problems on cyclic queuing networks, which are easier to solve. Right. So I'll take a short 2-minute break and I'll be back with these problems. No, everyone. So let's resume the discussion on closed cyclic networks. So we'll be solving a few problems. So okay. So let's actually try to derive a formula. So let's say we have a two node closed cyclic network, right? We have one node here. So this is node 1 with a single server serving rate mu1. And then this feeds into the second node, node 2, with a single server serving rate mu2. And then this essentially cycles back to the first node, right? And so that's all we need, right? And well, also the number of customers in all of the nodes combined, so like n1 plus n2. Let's say the total number of customers is always k. So this is known. And so what we want to find is the normalizing quantity, which is g of k, right? So if we remember from the theory, so we write the probability p n1, like we use this notation, n1 n2 equal to 1 by g of n1 n2. Yeah, there are two nodes, so it's 1 by g of k, and this one, rho 1 to the power n, rho 2 to the power, and n2 is, so if I write this properly, n1 plus n2 equal to k, and so I can actually, let me write it this way, g plus g of n1 plus n2, and then this will be rho 1 to the power n1, rho 2 to the power n2, right? And we know n1 plus n2 is equal to k, which implies I can write n2 as k minus n1. And so I can convert this into a single variable p of n1, something like k minus n1, equal to 1 by g of k, rho 1 to the power n1, rho 2 to the power k minus n1, right? And we want to find the value of g of k. So we can simply apply and we also have another relation, right? From the theory, from the balance equations, we can write rho. So for I equal to 2 to k, you can write it as mu I minus 1 by mu I, rho I minus 1, right? So rho 2 equal to mu 1 by mu 2 times rho 1 and rho 2 equal to mu 1 by mu 2 times rho 1, right? And we usually set, so if we usually set rho 1 equal to 1 for now, because ultimately we'll be normalizing, so it's fine, which implies rho 2 equal to mu 1 by mu 2, right? And so anyway, before using this, so we can actually sum over n1 equal to 0 to k, p n1, k minus n1, and this sum has to be equal to 1, right? So we can take 1 over g of k common from the from the denominator and write g of k as summation n1 equal to 0 to k. Now rho 1 is equal to 1. So 1 to the power n1 and rho 2 to the power k minus n1, right? So this sum actually is like a GP series, right? Because 1 to the power n1 is 1 and rho 2 to the power k minus n1 is rho 2 to the power 0 plus rho 2 to the power 1 till rho 2 to the power k. So it's the sum of it. So it's like it's 1 plus rho 2 plus rho 2 square plus rho 2 to the power k, which can be written as 1 minus rho 2 to the power k plus 1 by 1 minus rho 2, right? So this is the formula of g of k for a cyclic queue with 2 nodes in general. So I wanted to kind of derive this because we'll be needing this for various problems. Okay. So once we have g of k, we can actually put it in and solve for all of the state probabilities. That's all we need. So let's see. Let's consider a similar again two nodes, single server at each node, and customers. Let's say there are 4 customers, right? Let's say there are like 4 customers, and we have mu1 equal to 1/3, mu1 equal to, let's actually make it 5, mu2 equal to 6, and R1, 2 is equal to 1, R2, 1 equal to 1, right? Because from node 1, he'll be going to node 2, back to node 1. So it's very cycle. So the question is, what is the value of g of k? That's a normalization function, which is the value. So you can simply use the formula g of 4, because k is equal to 1 minus rho 2 to the power 5 by 1 minus rho 2. And here rho 2 is nothing but mu2 by, which is rho 2 is mu1 by mu2. So we can just use that. We can use this relation from the state transition diagrams, mu of I minus 1 by mu I. And we know rho 1 equal to 1. We usually set rho 1 equal to 1. So rho 2 equal to mu1 by mu2, which is nothing but 5 by 6. And so then this becomes a calculated job. And yeah, so if you do the calculation, we can get the answer. I can do the calculation quickly, but it's not particularly important. I usually like this make my own problem. So it's 1 minus, I think I missed. Yeah, so it's as I was discussing, it's 1 minus 5 by 6 whole to the power 5 divided by 1 minus 5 by 6, which is 1 by 6. So it becomes 6 times 1 minus 5 by 6, 5 to the power 5 by 6 whole to the power 5. And the answer comes out to be yeah. It's roughly 3.59. So yeah, so we can just do these kind of simple calculations, and we can, and then kind of we can, and then a follow-up question, right? Like now we know G of 4, so we know the normalization constant. So now we want to find out that what is the expected value of N1. So expected value of number of customers at N1. And so how do we find that out? So we denote, or like we actually denote it as in our lectures, we denote it as L1. Right? And so firstly, let us write down the state diagram. So it will be P of N1, 4 minus N1 equal to 1 by 3 point, it was actually coming out to be 3.588, because this is the normalization constant, times rho 1 is 1 and rho 2 is 5 by 6. So 5 by 6 to the power, or like if I write it as, instead of, I can make it as N2, 4 minus N2, N2, 4 minus, let's say N, N, so it will be N, right? N2 is N, N1 is 4 minus N, and so we can kind of write it in this way, right? So what is the state space that we have at the moment, right? So we can have, there are 4 customers in total. So we can have 0 in node 1, 4 in node 2, 1 in node 1, 3 in node 2. We can have 2 in both nodes. We can have 3 in node 1, 1 in node 2, or we can have all 4 customers in node 1. So this is a pretty simple exhaustive list of possibilities, right? So now let us, and I want to find the expected number of customers at node 1. I want to find N1. So here in this state, node 1 has 0 customers. So this probability doesn't count. So I need to, so my L1 will actually be 1 times probability of 1, 3 plus 2 times probability of 2, 2 plus 3 times probability of 3, 1 plus 4 times probability 4, 0, right? Because it's just a weighted average. So I'm just trying to find the probabilities of each of these states and adding the weights to the number of customers. And the first state doesn't count because there are 0 customers in node 1. So let's find out these probabilities. Right? So 1 times, so we'll have this 1 by G of k coming as common. So 1 by 3.588 times 1 times 5 by 6 whole cube plus 2 times 5 by 6 whole squared plus 3 times 5 by 6 plus 4 times 5 by 6 to the power 0. So that's 1. So we can quickly solve this. I'll be using the calculator. Okay. So the answer for this is coming to be roughly 2.36. In verify the calculations, as I said, I just looked at the others, but I'm just trying to emphasize on the approach here. So these are all the possible states that could have existed in this network. And so this is how I will just find the weighted average to predict how many customers are there in node one. And then as a follow-up to that, right, okay, so another question, an important question is actually this. So even the key really is to find out the steady state distribution, for which you need to correctly compute G of K. Once you have G of K, you have the steady state distribution, and then you can compute any quantity, right? So it's always 1 by G of K. So again, so this to clarify it again. So this maps to N1, this maps to N2. And we knew that N1 plus N2 is equal to 4 because there are total 4 customers in the system. And we always set rho 1 equal to 1. And so rho 2 becomes mu 1 by mu 2 from the balance equations. So this was a this was an important problem to solve. And then like we can also solve something similar, which is what is the probability that the second probability that node 2 is busy, right? So then this probability is actually the probability. So the probability that node 2 is busy equals probability L2 greater than 0, right? So because if there are no customers in node 2, it means that it's free, but we don't want that. Probability L2 greater than 0, so this we can write it as 1 minus the probability that L2 is equal to 0, right? So again, let us write down the state space here. So we had it as 0, 4, 1, 3, 2, 2, 3, 1, and 4, 0. So this is of the form N1, N2, right? And so not L2 as actually, the probability that N2 is greater than 0. L is the average quantity, so I just want to clarify the notation. So in all of these states, there is only one state where N2 is equal to 0, which is 4, 0. So let's find the probability of 4, 0, which is again from the formula is probability 4 minus n, n with n equal to 0. So it's 1 by 3.588, which is G of K times rho 2, which is 5 by 6 whole to the power 0. So that's just 1 by 3.588. And And this is actually also equal to probability n2 equal to 0, right? Because no other state has this property, which implies probability that node 2 is busy is equal to 1 minus 1 by 3.588. So let's see what this model is. This actually comes out to be approximately 0.72. So it's almost like 72% of the time in a cyclic queue with these parameters with two nodes, we'll find node 2 to be busy. So, unfortunately, like for this week's content, this is all I had to cover. There aren't many, as I was kind of discussing, there aren't many questions that you can solve on pen and paper um, um, from these topics, because these algorithms are indeed computationally heavy, and they have to be solved using computers. You have to write code to solve them. So I have covered some problems that can be solved mostly with closed cyclic networks. Motor property becomes simple. Don't have anything more to cover. So, and since no student has joined the class, I will end early. Thank you for watching. And I'll make the notes available as usual. I'll still hang on for a few minutes to see if some student joins. Um, I've uploaded. If I've uploaded the notes, I will end the call now. Okay.